Amedeo Avogadro, Counting the Invisible. Torino, early 19th century. In a city of priests, lawyers, and princes, chemistry is not yet the main attraction. You study law if you want a respectable life. You study theology if you want influence. You dabble in natural philosophy as a hobby, maybe. In a dim office lined with legal documents, a young man is doing exactly what his family expects of him. He's reading civil and ecclesiastical law, preparing for a career in the courts. On the table in front of him, statutes, commentaries, legal codes. On a shelf nearby, something less expected. Books on physics, on electricity, on chemistry. When no one is looking too hard, he reaches for those. His name is Lorenzo Romano Amedeo Carlo Avogadro. The world will remember only one of those names. It will attach it to a number so large it is almost comical, and to an idea so simple it took decades for people to fully accept it. Equal volumes of gas, under the same conditions, contain equal numbers of invisible things. Avogadro is born into nobility in Turin in 1776. His father is a prominent lawyer and politician. The path seems clear. Follow in his footsteps. Amedeo does exactly that at first. He earns a doctorate in law at a young age, practices, even teaches ecclesiastical law. Externally, their story is normal, but internally, something else is happening. He starts studying mathematics and physics on his own. No big declarations, no dramatic rebellion, just a steady shift in what he spends his time thinking about. Instead of only statutes, he reads about electricity, experiments with charges on conducting bodies, writes papers on physical topics. Gradually, the center of his life slides from the courtroom to the classroom, from codes to equations. He takes a position teaching physics and then mathematical physics. In an era when many natural philosophers are still part-time aristocrats or clergy, he's making a quiet pivot. The law of the land is giving way, in his mind, to laws of nature. By the time Avogadro is deeply engaged with science, chemistry has been transformed by people like Lavoisier. The language of elements and compounds has replaced alchemical jargon. Conservation of mass is accepted. Gases are no longer airs in vague categories, but substances like oxygen, hydrogen, nitrogen, carbon dioxide. Yet there is a mismatch in the way people talk about them. John Dalton has proposed that matter is made of indivisible atoms and that compounds form when atoms of different elements combine in simple numerical ratios. 2 hydrogen atoms and 1 oxygen atom make water, for example. Gay-Lussac has measured how gases combine by volume. He finds that, under the same temperature and pressure, gases react in simple volume ratios. 2 volumes of hydrogen gas react with 1 volume of oxygen gas to form 2 volumes of water vapor. Those numbers are so clean it is hard to ignore them. 2, 1, 2. But Dalton is cautious about treating gas volume as a direct measure of atomic count. He suspects that elements like hydrogen and oxygen exist as single atom particles in the gas phase. Dalton's atoms and Gay-Lussac's volumes do not line up neatly. If 1 volume of oxygen and 2 volumes of hydrogen produce 2 volumes of water, what does that say about the actual numbers of particles? Nobody has quite nailed it. Avogadro looks at this tangle and sees an opportunity. In 1811, Avogadro publishes a short paper with a long title in an Italian journal that will not have much international circulation. Inside it is a sentence that seems almost modest. He suggests that equal volumes of gas at the same temperature and pressure contain equal numbers of molecules. not equal masses, equal numbers. He also proposes a distinction Dalton has blurred. Atoms are the smallest units of elements that cannot be broken down chemically. Molecules are combinations of atoms that can be either elementary, like the particles of a pure gas, or compound, like the particles of a gas made of different elements. So hydrogen gas is made of hydrogen molecules, each containing more than one hydrogen atom. Same for oxygen gas. Under his hypothesis, when two volumes of hydrogen gas react with one volume of oxygen gas to form water vapor, the volume ratios reflect the ratios of molecules, not the ultimate atoms inside them. Two volumes of hydrogen gas contain twice as many hydrogen molecules as one volume of oxygen gas contains oxygen molecules. When they react, those molecules break apart and recombine. If hydrogen gas molecules are H2 and oxygen gas molecules are O2, then you can write 2 H2 in gas plus 1 O2 in gas equals to 2 H2O gas. Two hydrogen molecules plus one oxygen molecule give two water molecules. The volume ratios, the combining weights, the conservation of mass. All of it lines up. What looked messy under Dalton's assumptions becomes neat. Avogadro's move seems small. Allow elemental gases to be made of multi-atom molecules. But it solves several headaches at once. Why does nitrogen and hydrogen combine to form ammonia in a 1:3 volume ratio? Why do so many gaseous reactions yield simple volume relationships? If equal volumes have equal numbers of gas particles, and if those particles are multi-atom molecules, then volume ratios become counting ratios. Chemical equations become not just balance sheets of mass, but of actual invisible entities. Of course, Avogadro does not know the exact number in any one volume. He does not write down 6.022 times 10 to the power of 23. That constant will come later, from other hands. What he provides is the bridge concept. There is a proportionality between the volume of a gas and the number of microscopic units in it, at fixed temperature and pressure. If you double the volume, you double the count. If two gases occupy the same volume under the same conditions, they contain the same number of particles, even if their masses and chemical natures differ. This seems almost common sense once you accept it. At the time, it is contentious. You might think that such a neat idea would be immediately embraced. It isn't. Avogadro publishes in Italian, in a journal that many French and British chemists do not read. Dalton holds onto his own views. Confusion about atomic versus molecular weights lingers. Some chemists are uncomfortable with invisible molecules as anything more than convenient fictions. For decades, Avogadro's hypothesis sits in the literature like a useful tool left on a shelf. A few people notice, most do not. It takes until the 1860s, half a century later, for a new generation to dust it off. At the Karlsruhe Conference in 1860, a meeting of chemists wrestling with the chaos in atomic weights and formulas, a chemist named Stanislao Cannizzaro circulates a little pamphlet. In it, he uses Avogadro's idea systematically to distinguish between atoms and molecules, to assign consistent atomic weights, to clear up contradictions. For many attendees, it is a revelation. If you assume that equal volumes of gases contain equal numbers of molecules, you can sort out which formula makes sense. You can decide whether water is HO or H2O. You can disentangle atomic and molecular masses. Only then, long after Avogadro has died, do chemists begin to fully recognize the power of his proposal. Later, as kinetic theory develops, and as Planck and Einstein and others push physics into the microscopic realm, Avogadro's hypothesis becomes a cornerstone. The number of entities in 1 mole of a substance, the amount that contains as many units as there are atoms in 12 grams of carbon-12, is named Avogadro's number in his honor. You can argue about conventions. You cannot argue with this. Chemistry now has a way to connect grams on a scale to counts of invisible particles. In practical terms, what did Avogadro give chemists and physicists? He gave them permission to think like this. If I have 1 mole of oxygen gas and 1 mole of hydrogen gas, I do not just have masses. I have specific numbers of molecules. Vast but knowable. If equal volumes contain equal numbers of molecules, then the ratio of volumes tells me the ratio of molecules, and the measured masses tell me the relative masses of those molecules. A mole of gas at standard temperature and pressure occupies about 22.4 liters. That means every 22.4 liter balloon of any ideal gas holds roughly the same number of particles, whether it is helium, nitrogen, or carbon dioxide. This abstraction makes chemistry scalable. You can calculate how many grams of reactant you need, how much product you expect, how many molecules participate in a reaction. You can think of the behavior of gases in terms of average molecular motion, collisions, energies. The laws of Boyle, Charles, and Gay-Lussac about pressure, volume, and temperature acquire a deeper layer. You're not just juggling macroscopic quantities, but averages over enormous crowds of invisible actors that Avogadro has quietly admitted to the stage. Once you have reasonably consistent atomic weights and a sense of how many atoms or molecules sit in a given sample, a new question becomes natural. Is there a pattern in the elements themselves? Why does lithium behave like sodium and potassium? Why do chlorine, bromine, and iodine feel like a family? Can we arrange the elements in a way that reveals relationships, not just a list? Avogadro's idea does not directly build that table. But without a coherent system of atomic and molecular masses, such a table would be a mess. With his hypothesis, and with the work of those who revive and apply it, chemists can assign more reliable atomic weights. Oxygen is given a reference value. Other elements' weights are measured relative to it. Compounds' compositions are analyzed. Slowly, the numbers settle. Patterns begin to whisper from the data. In Russia, in the 1860s, a professor named Dmitry Mendeleev sits down with cards bearing the names and properties of known elements. Atomic weights, densities, valences, observed behaviors. He starts arranging them like a game of solitaire in order of increasing atomic weight, noticing how chemical properties repeat in regular intervals. When a pattern breaks, he is bold enough to leave gaps, to predict elements not yet discovered, to adjust some atomic weights he suspects are wrong. Behind his confidence in those weights is a whole century of work. Lavoisier's mass balances, Dalton's atoms, Avogadro's invisible counting, Canizzaro's clarifications. Mendeleev will turn that inheritance into something every chemistry classroom has on the wall: the periodic table. Avogadro did not get to see his name attached to a constant, or his hypothesis elevated to a postulate printed in textbooks. He died in 1856, before the Karlsruhe Conference, before Canizzaro's pamphlet, before the periodic system. For much of his life, he was a quiet, local figure. A professor in Turin, publishing in Italian, balancing teaching with modest experiments. Today, when students talk about a mole of something, or when chemists use Avogadro's number to switch between grams and particles, they are inhabiting a world that his simple, radical statement helped create. Equal volumes of gas at the same temperature and pressure contain equal numbers of molecules. He gave us a ruler for the invisible. Next time, we'll travel to Mendeleev's Russia. We'll sit at his desk as he shuffles cards with element names, weights, and properties late into the night. We'll watch him realize that if you arrange elements in order of increasing atomic weight, similarities recur in a rhythm, a periodicity, and that where the rhythm stumbles, nature might be hiding an undiscovered note. We'll talk about how he left spaces for elements that didn't yet have names, guessed their masses and behaviors, and how later discoveries filled those gaps almost exactly as he predicted. If Lavoisier weighted the air and Avogadro taught us to count its unseen particles, Mendeleev will show us how to put all those elements into order so that chemistry stops being a list of isolated facts and becomes a map.